Hi, good afternoon. So I'll be speaking about rainbow matchings, and this is a joint work with Shushmita Saket and Mehra. I'm Sanjukta. This is a joint work with Shushmita Saket and Mehra. So, okay. So the outline of the talk will be: I'll first be introducing the problem, then I will define. I will give a FPT. Thankfully, Jaykrishnan has already defined what is an FPT algorithm. So I will give an FPT algorithm for rainbow matching on parts, and then I will give a kernel. I will define what is a kernel for rainbow matching on general graphs, and then we will discuss some open problems. As we all know that maximum matching can be solved in m root n time, but when we add some additional constraint to maximum matching or any kind of matching problems, it turns to become NP hard. In the morning we have seen many matching problems. So few of the examples of NP hard matching problems are as follows. Is maximum matching, minimum maximum matching, induced matching, and our problem, rainbow matching, which we'll be talking about today. And this is a very classical problem. This has been mentioned in the classical Gary Johnston's book. So let's see what is the problem. So you are given an undirected graph and a coloring function which we are denoting by chi, and the colors are on edges. So this is the graph, and there are colors on edges, and as you can see from the picture, this is not a proper coloring, so that it could be any coloring on the edges. And so I have 1 to q colors here and a non-negative integer q, and the question we ask is that does there exist a colorful matching of size at least k? What is a colorful, what do you mean by colorful matching? So a colorful matching means all the edges have distinct colors in the matching. So if you look at the bold edges here, this red, purple and cyan, so they form a colorful matching. Now I want a colorful matching of size at least k, and as you can see that k has to be upper bounded by q because q is the total number of colors we have. So the parameter we'll be looking at is k. So let's look at some related works that has been done. So as I said that this is an old problem. So in JCM 78, this problem was shown to be NP hard for bipartite graphs, and this even turns better or worse, whatever you say. This problem turns out to be NP hard for very restricted classes of graphs such as paths, complete graphs, and when you have very small trees. So PHV trees means that you don't have long paths, and every color is used at most twice on the edges. Similarly, P5 free linear forests where every color is used twice. P4 free bipartite graphs, same, every color is used at most twice. So in very restricted setting also this problem becomes NP hard. So we turn to look at the parameterized complexity of this problem with the parameter solution size, that is k. So rainbow matching on general graph admits the star here means that I am hiding polylog factor here. So this has O star 2 power k algorithm, which is randomized, and this algorithm can be achieved by giving a reduction from 3 set packing. So so yeah, if the time complexity of that problem improves, then this will also improve. And the main two results that we'll be talking about today are these two. So rainbow matching on paths can be solved in golden ratio power k time in deterministic polynomial space, and on general graphs we will be looking at a kernel which has quadratic number of vertices and q vertices. So let's begin. So we'll first look at this problem. So look at this. To solve this problem, I'll be introducing another problem which is called disjoint, which is related to rainbow matching. So let's first define that problem. So this is what we are calling disjoint set rainbow matching problem. So you are given in this you are given a path. Obviously you have colors on the edges, and you are also given a set of paths, and these paths are vertex disjoint, mutually vertex disjoint, and it is also vertex disjoint from this path P. Okay, and now we again are given a non-negative integer k, and we ask the question that does there exist a colorful matching which takes exactly one edge from each of these paths and some edges from here such that the size of the matching is at least k. Okay, so our what is the rainbow matching problem? Rainbow matching problem, you are given some graph and you are asking does there exist a colorful matching of size k. Here I am given an extra set S and I have this extra restriction that I want at least every path have at most one, every path from S has at least exactly one edge into the solution. Okay, so now we see how you'll be defining a algorithm for rainbow matching on paths. So before that, we give this auxiliary graph for this disjoint. Given an input of disjoint set rainbow matching, we create this auxiliary graph, bipartite graph. How is this created? So we have this vertices for the color classes. So we had colors 1 to q, right? And we have this paths. So one partition of the bipartite graph is the colors 1 to q. Another partition is this paths p1 to p mod s, and we put edge between a color and path if this color appears on this path. So color 1 appears in p1, so we put an edge from 1 to p1. Color 2 also appears in p1, so we put an edge from 2 to p1, and so on. So this gives you a bipartite graph. Now it's not difficult to see here that if I find a matching saturating this set of vertices p1 to p mod s, then I get a colorful matching, right? I get a colorful matching which takes exactly one edge from here. How do you get that? If I take a matching saturating S here, so whichever color it is matched to, you pick that colored edge from here, right? And that will give you a matching because these paths are vertex disjoint. So you get a colorful matching which satisfy the constraint, right? So now we know that given this set S and this colors, we can find a colorful matching. The problem remains that I have also given this path P into this problem, right? And I have to find a colorful matching which is also compatible with this path. So we'll be giving a branching algorithm. But before we go into the branching algorithm, we'll look at some base cases. So the measure for the branching algorithm that will be used is k minus s. So you can for now ignore this. So the first sanity check that you do is that if this parameter is less than equals 1, so if this parameter is 0, right, that means your k is exactly modest. So you don't want any edge from the path that you are given, you just want as many edges from the set. So that as you saw in the previous slide, we can achieve that in polynomial time just by finding a matching in the auxiliary bipartite graph shown. So, and if it is less than 1, so we have to pick exactly one path from the path P, or one edge from the path P, and that we can do, so we pick every edge and see that if we can find a matching which does not have this color. So this, if the parameter is less than equals 1, then this can be done in polynomial time. Now let's look at this problem more clearly. So I have this path P and I have this set S, right? So now consider that suppose this edge vi plus 1, suppose this edge is in a solution of colorful matching, and from this prefix part we have at exactly one edge in the colorful matching. So if I know such an edge vi plus 1, so I can put vi plus 1 into this set S, and I can, since I know that this prefix has exactly one edge into the solution, I can also put this prefix into the set S, and then from all the paths here I will have at most one edge from each path, exactly one edge from each path, and from both of these two paths also I will have exactly one edge, right? So the maximum matching size for this the bipartite graph that we'll be constructing for S prime should be 2 more than the maximum matching size we had here, right? So if that condition does not satisfy, right, if it is less than equals to just plus 1, then we can say for every such edge vi plus 1, then we can say it is a no instance. So this is the intuition on which we will be branching. We will be in the branching algorithm, we will be looking for such an edge, So what is the property of this edge? This is the edge that goes into the solution, and the prefix path has exactly one edge into the solution. So let's look into the branching. So we have this path and we are branching on this edge vi plus 1, and so in one branch we decide that this path goes into the solution, and if it goes into the solution, then as I was showing that your S, we can modify S like this, that I add the prefix path into S and this edge into S, that's just that edge as a path into S, and I change the original path by removing the prefix till I plus 1. So this becomes the new instance, and the parameter mu changes by 2 because size of S changes by 2 and K does not change. Similarly, if this thing does not belong to the colorful matching, if this edge does not belong to the solution, then what I do, I know that this edge is not into the solution, so I know that from this part till pi I'll have one edge. Okay, so this is such an edge for which the prefix from the prefix exactly one edge goes into the solution, right? So from this part v1 to vi, I will have only one edge into the solution, so I add that into the set S, and the remaining path is what P is. So then my size of S increases by 1 and parameter K does not change. So the solution size K does not change. So the measure for the branching changes by 1. So we get a branching vector 2, 1, and it can be easily shown that this branching vector gives you this running time. Okay, so now we move on to the kernel for this problem, and before that I'll be defining what is a kernelization. So it's a polynomial time preprocessing where we give reduction rules. So this is so let's look at the picture. So I am given an instance of a parameterized problem. So I belongs to sigma star and K is an integer, and we have some reduction rule which produces another instance of the problem such that the parameter is bounded by some function, some computable function of this original parameter, and these two instances are equivalent. So what do you mean by these two instances are equivalent? This is that if ik is a yes instance, if and only if I prime k prime is a yes instance. Okay, so we say that this reduction rule is safe if this condition holds, that then a new produced instance is equivalent to the previous instance. Okay, so we'll be giving some reduction rules and we'll look at the safeness of the reduction rule, and we'll be when I say that it has a kernel of size order k square, that means I'm saying this I prime, the final I prime that we'll be producing, is bounded by order k prime square. Okay, so this is our goal for now, that we'll be looking at designing reduction rules such that we can bound the size of the problem, the input instance, by the quadratic of the parameter or the solution size. So the first reduction rule is this, that look at your graph and look at a particular color, look at the edges of that color. If you can find a matching of size 2k minus 1 of the edges that are there, then and you might have some other edges also, so some other edges of the same color, some other colors. Okay, so if the matching size is at least 2k minus 1, then I delete those edges. Why is this reduction rule safe? So I need to show that the equivalence, right, that we just talked about. So since there are 2k minus 1 edges here, okay, and I'm looking for a k size solution, right? So if I have one of the deleted edges, suppose I have and I'm reducing k by 1, Okay, so the parameter also reduces by 1. So essentially what I'm saying is that from this red color class, I'll always be able to pick a edge into my colorful solution. And why is that? Because I'm looking for a k-size solution. So suppose, if I remove this red edge, I have k minus 1 edges there, right? Which has 2k minus 2 endpoints. So since I have 2k minus 1 edges here, so at least one edge will be untouched. Like all those edges are not incident on at least one of this endpoints of one of these edges, right? So we can safely delete these red edges if I have a maximum matching of size this and reduce the parameter by 1. Okay, so after we have done with the reduction, for every color the maximum matching size is upper bounded by 2k minus 2, because if I had a maximum matching of size 2k minus 1, I have deleted those edges, right? So now we what we do is we try to greedily create a solution, and we'll see why this is useful. So this will lead us to a new reduction, a decomposition of the graph. So what we do, we try to greedily pick up a solution. So we just pick an edge and put this into the solution M. Say we are constructing this solution M, so we pick an edge and put this into M, and I have to delete all this blue color edges, right? If I put this blue color, because I'm not allowed to pick blue again, and also this two endpoints are not allowed to be part of any other edge. So what I do is I delete all these blue color edges, and I also delete all the edges incident on both the endpoints. Okay, so the graph will not be looking that fast, just that my figure has less edges. So we keep on doing this, okay, as long as we have no more edges left, and that gives me a matching M. Okay, now see what I have achieved by doing this. So let's say the colors that are present in M are some 1 to L, okay, and let's say the vertex cover of those color classes are denoted by xi. So the total vertex cover, if I belongs here, the vertex cover of that color class I'm denoting by xi. Okay, and so what happened? When did we stop adding edge to M? When the graph became empty, right? We added an edge to M, we keep on deleting the same colored edges and the edges incident on the endpoints, and the graph becomes empty. So since the graph becomes empty, means it has independent set of vertices, right? So that means if I take this set, okay, this gives me a vertex cover of the whole graph. Is that clear? Because this set union of IXI, this is the vertex cover of all the for the edges which are, these are covering of those edges which are of color 1 to L. Here I goes from 1 to L. Okay, so which are of color 1 to L, and vertex set of M covers every other edge. So this gives me a vertex cover of the graph. So now I get and what is the size of this? Because so if my M had at least M had size at least K, then we are done, right? Because we are looking for a colorful matching of size M, and colorful matching of size at least K. So M has size upper bounded by strictly less than K, and here I have, right. So here I have okay, so I'll be bounding this thing by order k square. We'll discuss why this is bounded by k in the next reduction rule. Sorry. So we'll be bounding this by k square, and then the remaining part is the independent set. So what remains is that to bound this independent set. So first I will show you that how we are bounding this by, so each of this xi will be bounding by k, and since L is less than k, so this will give me k square. So this whole term will be bounded by order k square, and then we will show that how to bound this independent set. So to see that, we give this reduction rule. So what are we saying here? Look at a vertex and look at the this in distinct colors incident on it. Okay, so the reduction rule is this, that if it has more than 3k minus 1, at least 3k minus 1 distinct colors incident on it, then I can delete a edge. Okay, so so why is this reduction rule correct? So suppose I deleted this edge, it has and the new graph has a colorful matching, then obviously the original graph also have a colorful matching, because the new graph is a subgraph of the original graph. So for the other direction, suppose the original graph has a colorful matching, and now that colorful matching, if that does not include this deleted edge, then that also gives me a colorful matching for the reduced graph. But if that includes this edge, then I must give you another colorful matching, right, or another solution. So what we do is that if this edge is included into that matching, now I have other k minus 1 edges, right? So all this k minus 1, so all this other k minus 1 edges, again, how many endpoints it has? 2k minus 2 edges, endpoints, right? So so since it has 2k minus 2 endpoints, and here how many colors you have? You have, this is the 3k minus 1, so you have 3k minus 2 colors remaining here, right? So from this for this 2k minus 2 edges, they can come here. So I'll just draw a picture here. There's no duster. Okay. So I have this vertex V, right, and I have some edges here which are of different some colors. Okay, now look at the look at the solution matching which included the deleted edge. Okay, so that edge, this is the edge that I deleted, so that edge is there into the matching. And how does the other matching edges look like? So the other matching edges can be like this, right? So how many endpoints from here is has this matching edges incident on it? It could be 2k minus 2, right? So 2k minus 2 endpoints here are already in the matching, in the solution matching. But I have how many colors here? I have 3k minus 2 colors left after deleting, at least 3k minus 2 colors left. So 3k minus 2 vertices here. So from that I am taking out this 2k minus 2. And how many colors I have used? I have also used k minus 1 colors. So also I take out k minus 1. So if you take out 2k minus 2 and k minus 1, you'll from this you will still be left with one edge and with one color that has not been used. So I can add that edge to this solution, and I'll get a new colorful matching. So this reduction rule is correct. So now, so after applying this reduction rule, what is it that we are getting? That for every vertex, the color degree is bounded by 3k minus 2. By color degree, I mean the distinct number of colors that are incident on the vertex phi, right? So, so the color degree is bounded by 3k minus 2. Right. So, okay. So we'll so next we'll look at a tool called expansion lemma. Maybe many of you are familiar with it, but I'll just state the lemma for the sake of whoever doesn't know, maybe. So first I define what is a Q star. So a Q star is a star which looks like this with Q leaves. So it's a key on vertices q plus 1 and it has q leaves. Okay. So next what I defined is called q expansion. So given a bipartite graph A union B and E, I set the subset of edges M star is called a q expansion from A into B of A into B if every edge. So here first let us look at an example, then we will read out the lines. So this is here I am showing a 2 expansion. Okay, so the blue edges are the edges of M star. Okay, so every vertex here from A has 2 neighbors in two blue edges going into B, right? So here if we are defining q expansion, so that then we will say that every edge of every vertex of A sees q vertices here or has q neighbors, blue neighbors here. So and what is the other property that, so this is what we call the q expansion, and the expansion lemma says that given a graph I can find set A prime and B prime such that there is a q expansion of A prime to B, and okay, there is a q expansion of A prime into B, and crucially the neighborhood of B prime is subset of A. Okay, so B does not see, A prime can see anything outside B prime, but B prime does not see anything outside A prime. So the neighborhood of B prime is contained inside A prime. Okay, so now we'll use this lemma to give a so as I said that we had one part, the vertex cover part, bounded by k square, and we wanted to bound the independent set size, right? So we'll use this lemma to bound the independent set. But before we go into there, we don't have a bipartite graph here, right? So here we need to construct like to use this lemma I need a bipartite graph. So we'll construct a bipartite graph and we'll use this lemma to bound the independent set. So for that, just some notation. So we define this CV to be the maximal set of distinct colors incident on a vertex phi. Okay, the colors incident on phi, basically you can think of this as. So now we'll construct this helper graph as follows. So we had these two sets, right? So I keep this set as one partition. So this independent set is exactly what B is, and I will construct a set A as follows. So I will use this vertex cover to construct the set A. So this vertex cover has two these sets, right? Xi union of this vertex covers of the color classes and vertices of M, right? So for every pick a vertex here which belongs to some XL, that is, it is a color it belongs to the vertex cover of color class L. For that we create a vertex here x comma L. Okay, so every vertex that belongs here, so for every vertex in Xi, for I going from 1 to L, sorry, I am using L twice. So every vertex in this set, I will create such an vertex here. So this vertex encodes the vertex and the color. And for every vertex from this set, okay, so say Y is a vertex here, and J is a color which is a color of Y. So that means there is a J colored edge incident on Y. So for that also I will create a vertex Y comma J. Okay, so for one vertex Y here, and for every J in CY I am creating such a vertex Y comma J, and so on. So now so now I have to define how I am defining the edges, right? So this defines how I am defining A and the set B. So now I will be defining the edges as follows. So I have an edge from this vertex V to Y comma J if Vy is edge of the original graph G, and this edge has color J. Then I will add this. Okay. So now that we have defined this graph, we can see that A is bounded by k square. Why? Because this set is bounded by k square, order k square, right? And between M and, so here how many colors I have? At most k, and here also I have at most k colors in M, right? So this total thing is bounded by order k square. Okay, right? So this is clear, right? A is bounded by k square. So now we are all set for applying the expansion lemma. So we'll apply expansion lemma on this graph, and we'll bound the size of the set B. So if B is already bounded by A, then we are none. So B is obviously greater than A. So I have these two sets, A and B, and we find a one expansion M star of A into B. Let's say this is A prime and B prime. Okay. So what is the property? That M star saturates A prime, and the neighborhood of B prime is subset of A prime. Right? This is just what we get from finding a one expansion. This is what we get from the definition of expansion, right? So now what expansion lemma said, that we can find such an expansion in polynomial time. So we can find the sets A prime and B prime in polynomial time. Now what is our reduction rule? The reduction rule is that if you have a vertex V here, which is not an endpoint of this matching edges, this one expansion edges, then we are deleting V. So before we look at why this reduction rule is safe, let's say that what it gives us. So if we delete such V, then if we keep applying this reduction rule, as long as B is greater than A, I know from expansion lemma that I will be able to find such set A prime and B prime, and we will be deleting this set. So finally the size of B will be deleting this such vertex V. So finally the size of B will be bounded by cardinality of A, which gives us since cardinality of A is bounded by k square, so this finally gives us a k square vertex kernel, right? So now let's see that why deleting this vertex V is safe. Okay. So again, suppose we have a colorful matching M of size k, and A prime M is the vertices of M, which are, so what did I do? I had this set A prime here, right? So look at this set A prime, and A prime has this vertex, sorry, this should be x comma I, y comma j, and z comma k. That's how I had defined. Sorry. So I had this x comma I vertex here. That means there is a vertex x in the original graph, right? So I collect all those vertices. That is this set, and that intersection, the vertex set of this colorful matching, is what I am calling A prime M. So this set here is A prime M. Okay, and now so which direction we are saying? So again, if the reduced graph, so what is the reduced graph? I have deleted the vertex V. So if the reduced graph have a colorful matching, then the original graph definitely have a colorful matching, because the reduced graph is again a subgraph. Now we are looking at if the original graph has a colorful matching, then I want to prove that the reduced graph also have a colorful matching. So this M is a colorful matching in the original graph. Now I have to show you that I can also find a colorful matching in the reduced graph. So when is that a problem? That's a problem if this particular vertex V is part of this matching M, right? So if this vertex is not part of matching M, then we are good. If it is part of matching M, then this is the mission. This is what I'll be describing, that how to find a colorful matching here. So if V is, so again I'll use the board. So what do you have? You have this colorful matching. So just imagine that these are of all different colors, and you have this vertex phi here. Okay, so this edge is part of this colorful matching, and now I have deleted this vertex. So in G prime, this edge cannot be there. So what I'm saying is that look at this set A prime M. Okay, you understood what is the set A prime M? I am taking intersection of the vertex set of M with the vertices that are present in A prime. Okay, so and consider those vertices here. So suppose those are these edges which are incident on this A prime, incident on the vertices of A prime M. Okay, so now what I will do is I will replace these edges by this blue edges. So what are these blue edges? Recall, these blue edges are the edges of the one expansion. So when I say I will be replacing this by blue edges, that means I will put xw into the solution, yu into the solution, zt into the solution, and so on, right? So and so I have to. So what I am doing, I am taking out these edges and I am putting those edges, right? Now I have to show that this new matching that I have created. Firstly, this is a matching and this is colorful. Okay. So to show that this is a matching, I have to show that these vertices are not present here, right? So since the neighborhood of B prime is contained inside A prime, okay, this is the property of the expansion. And the edges of the vertices of A prime are all present here, right? So no vertex of A prime is present outside here, right? So no vertex of A so no vertex here. These are the vertices of AM, right? So these vertices are not present here, okay? And this is the vertices of these are these vertices. They also do not see anybody here, so none of these edges are incident on them. Okay, so this is a matching. And why this is colorful? Because look at this. If I had a edge xv, then I am putting this edge xw. So xw was connected to xi. And how did we construct? From the construction of A, I know that if this edge is present, xi to w, that means this xw edge in the original graph has color I. So we are replacing with the same color. So this whole thing is colorful and this is a matching. So the new matching that I have produced is colorful and this and of equal size. So this gives you a colorful matching of size k into the reduced graph. So that proves the safeness of this reduction rule. Okay, so we have a k-square size kernel, and that finishes the results that I am supposed to present, and we'll look at some open problems now or some concluding remarks. So, as I said in the beginning that this problem rainbow matching has a randomized algorithm which is 2 power O star 2 power k. So that, and we get this randomized algorithm by giving a reduction from 3-set packing. Okay, so that I gave a reduction from from rainbow matching to 3-set packing, right? So that bounds rainbow matching in one side. Another problem from which you can give a reduction to rainbow matching is 3-dimensional matching. So I'll just explain quickly what the problem is. So it's like you can think of you have 3 types of set, and so this is like and you have a family where each family intersects each type at only one point. So you have 3 side sets, and you have in the family you have one vertex from one element from each of the type of the sets, and then we are looking for a subfamily that contains k pairwise disjoint sets.
right, of size at least k. So this problem can be reduced to rainbow matching. So this gives a bound on this thing. So, and all these problems, 3-set packing and all these problems have a history of randomized algorithm and deterministic algorithms that has been studied for this problem. So this paper, Zehabi in 2015 paper gave a deterministic algorithm of this running time, and I'm not sure if this is the current best or this has been improved. So given these scenarios, we ask that can we get a faster randomized or deterministic algorithm for rainbow matching or 3-dimensional matching? And we gave a k-square kernel for the general graph. Now can we, but we, as you saw that in the paths we get a very good FPT algorithm. So is it possible to get a better kernel for paths on rainbow matching? And also, can I have a 2 minus epsilon power n time algorithm for rainbow matching in general graphs?